seminar today. So the seminar will be given today by Alessandro Trinca, who recently graduated at the University of Rome in Sapienza, working with Schneider on high-energy galaxies and also the relationship between black holes and early galaxies, working with analytical models, and is now continuing in that direction at the Astronomical Observatory. And today he's going to talk about seeking the life of the early universe, cosmic technology.
Thank you, Lucio, for your very kind introduction, and thank you everyone and for having me here today. And today I'd like to give you an overview of this work that we've done in collaboration mainly with Raffaella Schneider and Rosa Valiante on developing a new semi-analytical model that we call Cosmic Archaeology tool to explore the early universe, and in particular to investigate the evolution of the first galaxies and black holes at high redshift. And when we started, Perfect. When we started this project, actually our main focus was on high redshift quasars. Basically, they are extremely bright active galactic nuclei powered by mass accretion on supermassive black holes with mass up to billion of solar. And we have hundreds of them observed so far within the first giga years of the universe evolution. And as you can see here, we have a compilation of the black hole masses estimated for some of these objects. As you can see, they span all over all up to redshift 8.7, where we have actually the one of the latest and for sure the farthest black hole ever observed just a few months ago, thanks to early JWST observations, which is at redshift 8.7. And so basically, one of the long-standing questions for theoretical model is, how do these kind of objects grow so fast in such a short time scale? But at the same time, if we look at the same distribution, but in terms of luminosity, we see that in the past few years, the detections, which are these bluish and reddish dots, enabled us to explore a much wider population of low luminosity AGNs powered by less massive black holes, down to very faint magnitude, in particular thanks to some dedicated surveys like the ShellQ one. And this is very important since this population of objects is a very promising candidate to explore the early mechanisms of black hole formation and growth. And this is also a very hot topic since we're starting to have the first detection of faint AGNs thanks to with JWST, and these are just some of the latest works on this topic, and we are starting to push down the minimum mass of black hole observed at very high redshift down to around 10 to the 6 solar, so closer to what is assumed to be the initial mass of the first black hole progenitors. But what is and in particular at the moment, the detection is based on the observation of broad components in the emission line of the host galaxies. But what is the theoretical picture for the evolution of this kind of objects? We assume usually that they evolve starting from less massive progenitors that we call black hole seeds. And in this nice picture from Metskuwa 2017, we see different possible channels of formation of these first black hole seeds, going from the most common one, which is the evolution of the first population of stars, so-called POP3 stars, which lead to remnants with mass up to a few hundred of solar, even a very high redshift, higher than 20. On the other hand, we can have much larger initial black hole seed mass in some very rare and peculiar condition, where we can have the so-called direct collapse scenario, where we have a monolithic collapse of an entire gas cloud in a single massive object up to 10 to the 5 solar masses. And in between, we have instead intermediate mass black hole formation, for instance, through runaway mergers inside very dense nuclear star clusters. But this concerns just the formation of the initial black hole seed. Then it has to accrete efficiently across cosmic time to reach the million or billion solar masses observed at redshift 6. And also in this case, we have different possible regimes of accretion. The standard picture is the Bondi accretion, where the black hole growth is mainly relies on the gas density in its surroundings, while at the same time, several simulations but also observations showed that in the case of large inflows of gas toward the black hole, we can have the building up of a optically thick accretion disk where part of the radiation is trapped. And so we can actually have some brief period at least of super-Eddington accretion with rates up to order of magnitude higher than the Eddington limit. But in order to study this broad framework of scenarios, we wanted to develop this new semi-analytical model called Cosmic Archaeology Tool, CAT, if you want, which is able to reconstruct the evolution of a large statistical sample of the entire galaxy population and follow its evolution during the first billion year of cosmic history. And in particular, is of course based on previous tools that we have extensively used to explore to reconstruct the evolution of the brightest and most extreme object that we observed around redshift 6 and 7, the most extreme quasars. But what we've done here is to extend this analysis to a much wider range of masses, and this enables us to follow the coevolution between the nuclear black holes and the host galaxies, going from the extremely small mini halos at very high redshift with mass around 10 to the 6 solar masses in dark matter, where the first POP3 star formation is supposed to take place, up to the very high, very massive overdensity where high redshift quasars are hosted at lower redshift. And the strength of this model is that at the same time, we are able to characterize in details on small scale the formation of both light black hole seeds, so POP3 remnants, and heavy black hole seeds through direct collapse scenarios, accordingly to the environmental condition of each galaxy. But on larger scale, we can make population study on a large sample of galaxies. And at first, we wanted to use this model to focus on the evolution of the black hole mass and luminosity function, with a particular interest in the still poorly constrained population of low mass and low luminosity AGNs. And to do so, basically, we had to at first calibrate the model properly. And we've done that in order to, on one hand, reconstruct the global star formation history of the galaxy population. And you can see on the left here, the star formation rate density versus redshift, where our predictions, which are the red lines, and in particular, the dashed red line, which is corrected for the observable galaxy population, compared with several empirical constraints. But on the other hand, we also wanted to reproduce the properties of the population of high redshift quasars. And for instance, here I'm showing you just as an example, the bolometric luminosity versus black hole mass relation, where our data sample is represented with colored dots for different redshift, and we compare with a compilation of observed quasar, which are the black dots. And while the gray dots are just for reference, some local observations. So once the model has been properly calibrated, the first thing that we've been able to reconstruct is the black hole mass function across cosmic time. So we have here the number density of objects as a function of their mass, going from redshift 18 down to redshift 4. And we assumed for our reference model a standard Bondi-Hoyle accretion capped by the Eddington limit. And what we can clearly see from this distribution is that black hole descending only from light seeds, which are the magenta points, and black hole descending from at least one heavy seed are clearly detached in the mass distribution. And this is telling us that actually light seeds are not able to grow efficiently through times in a standard accretion scenario. And of course, we compared these results, at least for the high mass end, with several both empirical but also theoretical results. In particular, in the upper panel, you see. Sure, please. Light seed for us is basically POP3 stellar remnants. So we have actually described the evolution of single POP3 stars and retrieved the final remnants of their evolution. While for heavy seeds, in the case we encounter in some galaxies the conditions, the rare condition for the formation of a direct collapse black hole, we actually plant a black hole seed with the initial mass of 10 to the 5 solar, and then we 10 to the 5. The other one is something like between 10 to the 2 and up to 3 times 10 to the 2. And then we follow their growth through accretion and mergers across cosmic times. And basically what we can see here is that we are pretty consistent with the several constraints from cosmological aerodynamical simulation in the upper panel. And instead, in the lower one, we compare with semi-analytical models. And the difference here, especially in the low mass end, are mainly given, as we will see in a moment, by the assumption that we made for the accretion process and the seeding scenario. We see that the higher number density of seeds starts to form around redshift 15. We have some early seeds in very high over densities already at redshift 17, 18, but then mostly around redshift 15, and then the metal enrichment is very fast and cuts down any possibility to form more seeds. Please.
Very nebulous.
Yeah, unfortunately, I went very rapid on the model, let's say, predictions and prescriptions. Sorry. Basically, we follow the metal enrichment in each galaxy, the star formation, the initial inflow of the baryonic component, star formation, then, of course, in a self-consistent way, also the feedback from stars and the central AGN, both metals, let's say, chemical enrichment, and also kinetic feedback. And basically, when we meet the conditions for heavy seeds, which are very low metallicity on one side, we have to be in large halos where atomic cooling is enabled. And at the same time, we also need to have a strong Lyman-Werner flux from nearby sources. At least we have a sort of homogeneous treatment for the background of radiation. But when we reach a given threshold of radiation and we meet the other condition, we plant a black hole seed, a heavy black hole seed. While for the light seed scenario, we just random sample the single POP3 stars formed at very high redshift, and accordingly to their time scale of evolution, then we evolve them and start to follow the remnant seeds. Sure, no, yeah. No, we actually, if we have atomic cooling halos, so with the virial temperature above 10 to the 4, with very low metallicities and enlightened by sufficient amount of Lyman-Werner flux, we actually form a seed that we plant in the center of the halo, and we start to follow its accretion accordingly to the gas, then the amount of gas and the gas distribution inside the galaxy. This is basically yeah, sure. We rely on merger tree from a press sector formalism, and we apply on that all the code for the baryonic evolution. Sure. No, don't worry.
The Lyman-Werner,
Mm-hmm.
do you follow it as a background, or is it actually in this there is no thought?
We follow that consistently with the source that we have in each merger through our simulation, but we do not have information on the spatial position of the sources, so we just average the Lyman background in the single merger tree. However, we have a sort of, we can actually make a statistical study because we have different merger tree of different masses, so in certain over density, the average Lyman-Werner will be much higher with respect to others, and so we can follow a sort of statistics of this kind of over density, but we do not have, of course, the information of the position of different sources in the single simulation. Yeah. The threshold has been is a free parameter. Of course, we have, of course, a homogeneous treatment, so we have to put a free parameter on that, which is calibrated in order to reproduce the observed properties of high redshift quasar for the most massive over density that we actually treat. Yeah, the number density of brightest objects, and then we see what are the prediction for all the rest of the population, especially for all this faint low mass population that we're starting to observe. And so basically, but we want also to know how that this mass distribution translates in luminosities. So we reconstructed also the AGN luminosity function in different bands, and I'm showing you here the X-ray luminosity distribution between redshift 4 and 6, where our predictions are the black dots and are compared with with several empirical constraints. And you can see that actually we find a very good agreement in the bright end of the distribution, especially when we account for quasar obscuration, which lowers the distribution as shown by the gray shaded area. But at the same time, we see that this stunted growth of LiDAR seeds is reflected in the luminosity function, and we predict this sort of sharp drop of the distribution below a certain luminosity. No, don't worry. No, this is the prediction, because actually the parameters are tuned only to reproduce some global properties as the mass and dust content, gas content of the rarest quasars that we observe, but only for the more massive overdensities. Then we expand the analysis down to a much wider range of masses where we do not have put any constraint apart from the fact that the global star formation history is consistent with the empirical results, but we do not put any constraints for the black hole population. And we see that, in fact, we find at least for the bright end where we have constraints that we are pretty consistent going to fainter magnitudes. But however, we have this characteristic features, this sharp drop in very faint luminosity regimes, and we will go back on that in a few slides. So, but at this point, we also wanted to understand what if we assume a different accretion scenario for the black hole population. So we made a very simplified model where we assume that the black hole growth is mainly driven by brief periods of enhanced accretion triggered by major galaxy mergers, during which we assume that a large amount of gas are funneled in the central region, so we can have we assume a slim disk model, and we allow the black hole, the central seed, to accrete a fraction of the available gas mass in the galaxy. And we see that just by applying this simplified scenario of accretion, we are able, on one side, to reconstruct pretty well at least the shape of the black hole mass function with respect to the reference model, which is the red dashed line in the high mass end. But at the same time, light seeds are now able to grow very efficiently and to bridge this gap between the two populations. And not only actually, because we see that we have now a mixed population of seeds, so also seeds descending only from light seeds, which have grown very efficiently during cosmic times. And a large fraction of the more massive system that we observe, especially above redshift 6, is composed actually only from very efficiently grown light seeds.
You assume that how do you measure the available
Yeah, this has been done. Of course, we have calibrated that on previous work done, especially on the super red neutron accretion scenario for very bright quasars. So of course, we here there is the possibility, of course, that we are overestimating the accretion of smaller seed, and for that reason, actually putting some constraints which are consistent with cosmological zoom-in simulation would be very beneficial. But at least for the high mass regime, we find a pretty good consistency with, let's say, with the simplified model, we are able to reconstruct the mass function just by changing a lot. So the high mass end seems to be not so sensitive to the underlying accretion model in a certain sense, while the low mass end it is allowed because we do not see anymore a sharp drop in the number density of sources. But the interesting thing is to see how this changes the distribution in luminosity, of course. And, we look at the available gas mass in cold gas, and we actually take a cold gas, yes, in the galaxy, and we actually take a very relatively conservative time scale for the accretion process, because we have this for these brief periods of enhanced accretion, this burst of accretion following a major galaxy mergers, and we enable the black hole to accrete a fraction a given fraction, which is a free parameter of the model of the gas available in cold form, but on time scale, which are given and are relatively of the order of 10 million years. So this is pretty let's say, conservative with respect to some simulation that show the characteristic time scale for the accretion might be also shorter. But of course, for the lightest black hole seed, there are a lot of caveats on that. But how that translates into the luminosity function is just to compare the two X-ray distribution between redshift 4 and 6. And we see that on one side, we have a strong signal, which is the fact that we do not have anymore this sharp drop in the luminosity function, but a sort of smooth decline. But unfortunately, this very significant feature relies on very faint luminosities. Just as an example, the vertical dotted line is the predicted luminosity limit for LINX mission, which is one of the deepest X-ray surveys that we might be able to have in the future. But at the same time, we see also some differences, especially in the normalization in the high mass, in the bright end of distribution. But here we need an improved modeling for this brief period of enhanced accretion and for their sampling in order to make stronger constraints. But at the same time, so it would be difficult to find some characteristic feature determining the underlying accretion model in the luminosity function. But at the same time, we have some strong imprints also on the global coevolution process with the host galaxy, and therefore, in particular, on the scaling relations. And you can see here the comparison between redshift 7 and redshift 5 of the black hole mass versus stellar mass relation for the two models. And you can clearly see the two detached population of seeds in one case and the mixed population of seeds in the other one. And in the case of a standard Bondi accretion, we see a sort of symbiotic evolution between the black hole and the host galaxy, while we have a sort of black hole dominance if we enable for super Eddington accretion scenarios. And this is very interesting since the latest, some of the first JWST observation of this faint high redshift black hole seems to suggest that some of them are overmassive with respect to the stellar component. And as if you focus on the upper points there, they are overmassive with respect both to the local scaling relation, which is given by the black dashed line, but also with respect to our reference model sample, which are the red dots. And if you compare that with the previous distribution, you see that these black holes basically are occupying the region of the plane where we predict the super Eddington population, let's say, to be. So it might be a possible initial hint of some super Eddington evolutionary history, but of course we need more observation to claim that. From the broadening of the broadening. And also, of course, some kind of uncertainties of the order of 0.5 dex, as always. So, yeah. Mm-hmm. Because actually, we assume a given distribution of the gas density, and based on that, and constraining the gas distribution in a fraction of the virial halo of the virial radius. We actually measure the gas density in the inner region around the black hole, which is basically calibrated with a standard free parameter, which is always used in semi-analytical model to account for the enhanced gas density in the very inner region that we are not able to. No, we are assuming actually we have both a hot and cold gas fraction because we actually follow also a little bit the cooling time scales of the gas inside the galaxy. But for the black hole accretion, we take the overall amount of gas, assume this density distribution, and from that we measure the Bondi accretion rate. Yes. No, we actually take all the gas from in the galaxy for the black hole accretion. What? Sorry? Yeah, we may overestimate that. But of course, the point is that there you have a large uncertainty on the very inner region density of the gas. So basically, we resolve just the galaxy and its properties. So it's not feasible to make some more accurate prescription for that, because you are always limited by the fact that you do not resolve the distribution of the gas. So we put there a free parameter accounting for all that mechanisms that are under our resolution, let's say. And so just to sum up what are our predictions for the overall AGN population, we see that the signature of the dominant, there might be some strong signatures of the dominant growth mechanism of the early black holes, but they might be hidden in a very low luminosity regime and challenging to test observationally. But at the same time, we start to have some imprints or some insights already on the coevolution process between the nuclear black hole and the host galaxy, thanks to JWST observations. And so we wanted to do a follow-up project on the observability of these accreting black holes with JWST, and in particular asking ourselves how many black holes we will be able to observe with different JWST surveys. And in order to do that, basically we reconstructed the number of objects per field of view of the NIRCam instrument predicted for different luminosity bands and different redshift ranges. And as you can see that here, given by the histograms, where the filled histograms, let's say the gray histograms are the population of unobscured objects, while the empty ones are the intrinsic population of quasars. So we apply the correction for the obscure fraction. And we compare that with the different colored line, which are the expected limits for the different surveys, both concerning the limiting magnitude and also the area coverage. And what we see is that actually this survey seems to be very complementary, and some of them, like the JADE survey, will go very deep and be able to probe maybe accreting black holes up to redshift 13, and others will go instead very broad and will be more sensitive to the rarest and brightest AGN that we have in the population. But the main point here is that we want to know if this observation may be able to characterize these accreting black holes in their pristine environments in order to constrain a little bit their nature and their formation environments. And so what we've done here is to measure the cumulative distribution of the population above a certain luminosity and divide the overall population in different bins of black hole mass, and compare again this with the sensitivity limits of the different surveys. And what we see is that between redshift 10 and 7, the JWST surveys are statistically more sensitive to black holes in the range of between 10 to the 6 and 10 to the 8 solar masses, while if we'll be able to observe systems above redshift 10, we have a higher chance to see them with characteristic masses below 10 to the 6, and so we will be very close to what is assumed to be the initial mass of, for instance, heavy black hole seeds. And we wanted to do the same analysis also for the properties of the host galaxy. And I'm showing you here the metallicity distribution again, and we find similar results, meaning that above redshift 10, we have higher chances to observe system in very pristine gas conditions below 10 to the minus 2 solar metallicities. And we've done that also for the stellar mass properties of the galaxy. Yeah. Mm-hmm. Yes, actually, we yeah, sure. Sorry, we take the reference model as a standard for all our prediction that I'm going to show you, because of course the Super Eddington one is a sort of simplified model to see what is the impact of different accretion model on the overall population. But to make stronger constraints on that, we need an improved modeling of this brief period of accretion, and we're currently working on that. But we don't trust the results too much to make prediction for JWST on other observatories. So everything will be based on the reference model from now on. But of course, all these predictions that I showed you based on a strong assumption which is that we will be able to identify with proper selection criteria this kind of galaxies hosting active black holes at their redshift. And it might not always be the case, since several works showed that the standard diagnostic diagrams that we use at lower redshift, like the BPT diagram and the OH over NO diagram, fail in clearly discerning the population of AGN from galaxy hosting AGN from a a global star-forming galaxy population. And we can see that clearly in the left panel, where we have this compilation of galaxies hosting active AGNs in red, while a more global, common star formation galaxy population is given by the bluish dots, and we see that they occupy the same region in the plane, while the black line is supposed to divide the region where AGNs and star-forming galaxies are. So probably, and the same result, we are obtaining the same results from some preliminary prediction made relying on the cut results and applying some spectral synthesis model, and we find our population to be in the same region. So basically, probably we will need some dedicated diagnostics in order to actually detect the presence of accreting black holes in these high redshift galaxies. But we focus so far only on the AGN component. Actually, CAT is a very powerful tool also to explore the evolution of the overall galaxy population at higher redshift. And in particular, in this work that just went on the archives 2 days ago, we wanted to focus on the bright galaxies that we are starting to observe above redshift 10. And to constrain some properties of these galaxies. In particular, here I'm showing you the galaxy UV luminosity function that we obtained from the model, and which are our prediction are actually the black points and are compared with several empirical constraints where at a redshift higher than 9, we have basically early GWST observations. And as you can see, we find a very good match with all these results up to around redshift 9, where we start to see an undersampling of the number of bright galaxies with respect to observations. But this is not just a peculiar feature of our model, but it has been shown that it's a common trend among many numerical models. And in particular, there have been a lot of work trying to explain these differences, and someone also claims some tension with the lambda CDI model. But however, it must be stressed that some of these extremely high redshift sources still lack spectroscopic confirmation. And one of them, for instance, on which these values at redshift above 14 has been based, has been revised to be at redshift 5 instead of 15. So we have to be very careful on comparing model with observation still. And for this reason, there is a lot of discussion in the community, and other works show that not only there is no tension at all with the lambda CDI model, but also already standard cosmological simulation can reproduce the observed galaxy number density. But what we wanted to do is some kind of tension still seems to be there, some kind of bright excess. And so we wanted to test which can be the impact of AGNs and early stellar population on the galaxy luminosity function. And what I'm showing you here is the total luminosity function. So considering also the AGN contribution for each source, and basically in the lower histogram, you see the relative contribution of the AGN emission in the UV with respect to the total, the mean contribution in bluish histogram, and the maximum contribution for each beam of luminosity in the empty ones. And you can see that a higher redshift, up to redshift 9, we can have some significant contribution of AGN emission in the bright range of luminosities. But if we go above redshift 10, they start to become negligible. So AGN cannot explain this discrepancy between models and data. But at the same time, we also see that POP3 stars, POP3 star formation survives down to very low redshift. And if we focus on the bottom panel, you can see that our prediction, which are the yellow line, which is the yellow line, which are compared with several other models, but there is this common trend of a star formation rate density which survives down to redshift 10. So we wanted to see what is the contribution also of POP3 stars in these early bright galaxies. And so I'm showing you here again the luminosity function of galaxies between redshift 10 and 20 this time. And on the bottom panel, you have the occupation fraction, let's say, of active POP3 stellar population in each beam of luminosity. And we see that down to redshift 16, we still have a non-negligible fraction of galaxies hosting active POP3 stars, even for the brightest beams of magnitude. But then we have a sharp drop in the occupation fraction, and metal enrichment take place very efficiently. And so we do not have any more POP3 stars, at least in the observable range of galaxy luminosities. But this is telling us something, actually. So POP3 star might not be might not give a relevant contribution, but some cosmological simulations show that actually the transition in the IMF between the very top heavy IMF that we expect for early galaxies and the IMF, the later IMF that we have in the local universe, might be much smoother. And as you can see here, there are some results from hydrodynamical simulation from Chon et al. 2022, and you can see how the IMF varies as a function of both metallicity and redshift as a result of the CMB acting as a floor of temperature during the process of cooling and star formation. And we see that there might be a high mass component surviving also both at a very low redshift in case, of course, of low metallicity, but also at higher enriched systems, but at higher redshift. And this is important because this might change the mass to light ratio in the observed stellar population. And so this might enhance the luminosity of our galaxy. And so we decided to correct basically our galaxy luminosity function for this sort of composite IMF, which depends both on metallicity and redshift. And you see that the luminosity function is shifted toward higher values as shown by this gray shaded area. But of course, we want to quantify the impact of this kind of correction. And so we try to compare, we focused on a given magnitude for our galaxy sample around -20. And we compared basically our prediction for the number density of galaxies for the stellar only case, stars plus AGN, and also for the stellar only case, but with this correction for a composite and evolving IMF. We compared them with some prediction from the best fit distribution obtained by observation. And we see that if we apply this correction basically up to redshift 13, our results are pretty consistent with data. While at redshift above 14, we have the discrepancy is reduced to 0.5 dex. However, it must be said that these light green lines are basically instead the number density obtained assuming only spectroscopically confirmed sources, and you can see that the difference is important, and therefore we need a larger sample of spectroscopically confirmed galaxies in order to tell if actually there is some tension in this high redshift regime. And just a few minutes, I will also like to show you how tools like CAT can be used also to probe the properties of the first stellar population and black holes using independent probes like the 21 centimeter signal, on which we focused on this work with a former master student, Emanuele Ventura, where basically, of course, the 21 centimeter signal came from the Haber-Fine line transition of the neutral hydrogen. And what we can observationally measure is the differential brightness temperature here between the 21 centimeter signal and the CMB. And basically it depends on a lot of properties of the global evolution of the intergalactic medium, but also on the properties of the first sources which emit radiation in a high redshift universe. And we've been able to recover also these properties from our model and to make some prediction for this 21 centimeter signal, which is just focused on the thick black line in these two panels. And what we find is basically that there is a strong dependence both on the kind of source that we consider, and especially in the form of the signal, we find the POP3 stars and nearly accreting black holes impact a lot the steep drop of the signal at the subsequent steep raise. At the same time, also the environments where this kind of sources are formed have a large impact, because if we exclude mini halos, which are usually not resolved, for instance, by cosmological simulations, the results are very different. But of course, if you want to include AGN to measure this kind of the contribution of AGN, you actually have to account for an additional potential radio background in this case, other than the CMB. And so we we applied this additional background to the model, and the main take-home message here is that if you properly calibrate both the radio emission and X-ray emission from our population of sources, you can be able to match the only available empirical constraints so far on the 21 centimeter signal, which is the one from the EDGES collaboration, which is still very disputed though. But the point is that with more precise measurement in the future, we might be able to constrain the mode, put some constraint at least on the mode of accretion of these first black holes and on the properties of their POP3 progenitors. No, basically it's just a simplified model where we, depending on the accretion on single sources, we applied a radio background proportional to the accretion rate, and actually we've done that, and this sum up to the CMB background against which we are measuring the 21 centimeter signal, and basically we've done that also for only some fraction of the black hole population for the highly accreting fraction, and see how that the initial signal, which is the very shallow line up there, changes. Yeah, from the jets. Yeah. Yeah. Yeah, basically it's calibrated with there is a degree of freedom, of course, in this, but it's calibrated on low redshift emissions. But the point is that basically improving the modeling from this kind of sources and having tighter constraints on this kind of signal, we can say something about the properties of these extremely high redshift sources. We are talking about redshift around 20. So some properties of the first POP3 stars and their remnant, which if they are able to accrete efficiently, they will have a strong impact on the IGM. And so we have this very steep feature given by the quick heating of the IGM given by the X-ray emission from small accreting black holes. And so I hope I convince you a little bit that this tool is very powerful to make prediction, not only for the black hole population and different channels of black hole seed formation and growth, but also for make some prediction on the detectability of the accreting black hole with current and for coming surveys. And at the same time, also to track the evolution of the overall galaxy population across cosmic time, and to develop potentially some diagnostics to understand the contribution of AGNs and the early stellar populations to the galaxy emission. And finally, to constrain also the properties of this first generation of stars through independent probes. And just to give you a snapshot on what are our ongoing developments, we are basically putting together our prediction and some modeling of the CID of our SED of our black hole sample in order to test the actually efficiency of current color selection criteria and try to develop some dedicated diagnostic to detect this kind of highly accreting black holes with JWST on similar surveys. But we also want to add some additional dynamical channel for the black hole seed information. And at the same time, finally, we are improving the treatment of the black hole dynamics, because this tool might be very useful to make prediction of the the number of gravitational wave events that will be observable with further interferometers, so both with LISA and the Einstein telescope. And unfortunately, Rosa couldn't be here today to give you more insights on that. So thanks for your attention. These are the reference of the work I present to you. Please. Thank you. Yep. Yeah, actually, the point is that I mean, we assume a given profile for this kind of galaxies, and of course, that profile relies on more local estimation. Then you cannot know what is the actual gas distribution at very high ratio where you have a lot of dynamical interaction. So that's true for sure. And the point there is that, of course, you don't know if it scales down, the same profile scales down to lower mass galaxies. But what we see is that actually in a standard accretion scenario, black holes are able to grow efficiently only when they are massive enough. So they start from heavy seeds, and they are located inside already evolved galaxies, or basically massive galaxies with let's say more similar to the local, or let's say to what we observe for high redshift AGN host. So this is true that you do not know how the accretion scales at in lower regime of mass and a higher redshift, but the very efficient accretion of these black holes happens only in the case of Bundy accretion scenario in more evolved and let's say presently like galaxies. Yeah, we do not test that for sure. In that case, this would be conservative, I guess. So of course you can have a higher. But the point is that of course then we have some free parameter on that. So of course in that case you would have just a lower boost of accretion given by the fact that you have a larger amount of gas in the central region. So we incorporate all that unknown physics in a standard free parameter, which is basically what other state-of-the-art semi-analytical models do, because if you do not have any underlying information on the distribution of gas, you cannot do much. No.
I guess the question is, if you would vary that, maybe the accretion more efficient, could you reconcile the AWS black hole in stellar mass?
Yeah, but at the point you would exceed probably the typical mass and properties of the high redshift quasar sample, and at the same time you will have a lowering of the stellar mass and galaxy and overall gas component in the brightest galaxy, because you will have an impact too strong of the AGN in more evolved system. So the point is that the strength of this model is that we follow different kind of processes, and they are all very linked. So making sure that the overall galaxy population is consistent actually gives some constraint also on how much the black hole may evolve efficiently, because otherwise everything gets disrupted. We can try if we have a common match between the two things. Yeah, it would be nice. Yeah. Now, at the moment, the model is very simplified for the dynamic. I mean, we assume that only if we have major merger events, the typical time scale of the merger is short enough to consider the two central black hole of the galaxy to merge in a realistic time scale. And we're working on that to apply a more detailed description for that, also to make LISA catalogs. And basically, just to give you an idea, these are extremely preliminary results, but this is what we are able to predict for in a previous work from Valiante 2018. We have the redshift versus total black hole mass of the system distribution, and we have the sensitivity curves, signal to noise sensitivity curves of LISA and the INT telescope. And what we can do now is to make some prediction on the merger rates for each point of this plane. But of course, we need this improved delay treatment, and we work in both on our side, but also to a common treatment of the delays for all the semi-analytical model with the LISA massive black hole catalog group. No, we have to improve on that side, but we are currently working on that. And you can see here that we are just some prediction assuming instantaneous merging. But of course, when we have this delay, we'll compare them with a lot of different probes. Sure. Sure.
Yeah. So here the heating is dominated by.
Yeah, here we have that very early POP3 stellar formation leads to this very sharp drop in the signal at early times, but then their remnant, if they're able to accrete efficiently, and then of course these are small black holes, so they might not be located exactly in the center of the galaxy. You have a lot of dynamical interaction, but if they accrete, actually they have a large impact on the IGM temperature, and this leads to this very sharp enhancement in sharp rise of the signal again. No, this is just for POP3 seed, because heavy seeds start to form just below redshift 16 for what matters. And their remnants, yes, or primordial black holes or whatever is already there. But of course, this is this depends strongly, as you saw, on the radio background, because this might be a huge impact on that. But this depends actually on the mode of accretion, mostly of these black holes. Yeah, we will link that to the X-ray luminosity, exactly. Yeah, I think that Emanuele Ventura is actually the expert on that, but they should be linked to lower redshift observation. So you do not know if that scales also down to this this kind of system, which are much smaller, might be different both for a lot of reasons, but at least it seems to be, if there is any radio contribution, it's very important. And if we, and in order to reach the very deep signal of edges, we would need at least some kind of radio background, because otherwise we never manage. Of course, this is a very controversial result with this the edges collaboration, but the point is that we might be able to probably calibrate the X-ray and radio heating to match that. Some work claim that you have to consider, if you have an efficient X-ray heating of the IGM, you have to also to consider probably a radio contribution, at least for the highly accreting object. But then we do not have strong constraints on that.
How much percentage is needed as a fraction of total time?
Which is the typical time scale of super Eddington accretion. Yeah, actually, what we assume is that if we have a major merger event between galaxies, for a given time, for basically for very short time scale, with a typical accretion time scale of the order of 10 million years, we have the black hole to consume a given fraction of the gas, of the available gas. And what we see is that actually these brief periods of accretion dominate the overall black hole growth across cosmic time, since the quiescent mode of accretion is not relevant anymore if we have this. Of course, you would need to have this very strong inflows of gas subsequently to major merger galaxy events.
That's it. We just have to be black hole seeds in the reference model. Cannot go there. So what's the real reason?
Basically, the reason is that if you look at the I have it here, the Bondi prescription, the standard Bondi prescription for the accretion we have here. You can see it here. This depends on the black hole mass squared. So basically, even in the case of gas-rich systems, you cannot manage to grow efficiently through that short cosmic time and reach masses higher than 10 to the 4 if you start from 10 to the 2 something times. In the Super Eddington case, we used that for the quiescent mode, but we also use this simplified model when we have major galaxy mergers. And we see that in this case, the brief period of accretion dominates completely the accretion history. No, we assume it when the galaxy is in a quiescent mode. When we have a major merger for a brief time, we assume instead a bursted accretion rate. We assume, we assume a slim disk, and all the luminosity prediction that I showed you are considered assuming a slim disk, so a reduced relative efficiency. Yeah. Everything, yeah. Yeah, basically, we see such a sort of similar behavior because actually we follow also the evacuation of the gas due to supernova feedback and AGN feedback. So in smaller halos, we actually find that light seeds or whatever kind of seed is not able to grow efficiently. And the point is that when this kind of system merge with gas-rich galaxies, you can have an enhanced. Yeah. Mm-hmm. Yeah. That might be very interesting. We didn't do that at the moment. However, we have to. The point is that there are the very bright systems that we find in the Super Eddington scenario depends a lot on how you model the luminosity during this period of accretion. And you can be subject to strong obscuration maybe. So we prefer at first to have a more constrained model for the Super Eddington and then go to make some predictions also on the galaxy population. Thank you.